Hi there. Let's use this practice test to review some of the concepts in electricity for topics 6, 7, and 8. And so what I'll do here is I'll go through some of the questions and try and provide a detailed explanation regarding what the answer should be and why. So the first question, what factor below does not affect the strength of an electromagnet? So let's look at a picture of the electromagnet again. Here's our electromagnet. And so as you know, we put a battery here and electricity runs, this has got to be down at the negative, runs from the negative through the coiled wire back to the positive. And when that happens, the center here magnetizes and creates a magnetic field. So you can start to pick up things like paper clips or whatever. So how do we change the strength of this? We could put more coils of wire. We could have, iron is the best core, but believe it or not, you could use other cores. And so that would weaken it. Iron would be the best. We could strengthen the size of the cell or battery. And so let's go to the question. So which of these does not affect the amount of current? Well, that would be strengthening the battery, so that does. The direction of current, that doesn't really matter. So the thing that does not affect the strength of the electromagnet would be the direction of the current. Number of coils, we just talked about that. That would strengthen it. And the type of core, iron's best. Next, let's look at number 2. A magnet can induce a voltage in a wire, which is the potential difference. How does this happen? So the question is, how does a magnet create voltage in a wire? Basically, what they're talking about here is a generator. So let's go back to my pictures. Here is an example based on work by Faraday right here of how a generator might work. And so if we move the magnet quickly in and out, that pushes electrons and creates a voltage on our voltmeter and a current for that matter. So the quicker we can move it in and out of this coiled wire, the greater voltage. So let's see which one applies to that. When either the magnet or the wire move at an angle. No, not an angle. When either the magnet or the wire move parallel. There it is. Yeah, so that's how we generate electricity using a generator. Only when the wire moves? No. Only when the magnet moves? No. So you could move the magnet, which is what I showed you, but you could also instead have a magnetic field, a horseshoe magnet, and you could parallel spin wire inside instead. So it works both ways. Next, a light bulb is rated at 100 watts if it A must operate from a 100 volt supply. No. Draws a current of 100 amps. No, not necessarily. The word watt actually means joules per second. Okay, so a watt equals so many joules per second. Okay, watt is a unit for power, and if you remember, we have two formulas for power. Power is joules divided by time in seconds, or we could also calculate power by taking the voltage and timesing it by the current. So the answer would be D, transforms 100 joules of electricity energy per second. Okay, that's what watts really means. What's the function of a ground wire in an electrical current? A ground wire. Let's go back to my pictures. So here's a little picture showing you that the plug-in here doesn't have a third prong, which would be a ground, and So this guy's holding the electrical appliance, and the joke here is he's going to get shocked. So ground wires are important because they provide a path should the electricity coming from the red hot wire, should it somehow jump, the ground wire would provide a path for it to jump instead of shocking you. So let's go back to the thing. So a ground wire reduces the risk of electrical shock. Next, thermal pollution from generating plants. How is it controlled? Let's go to this page in our books. Somewhere here. I had a second page if I can find it. Okay, I'll have to go here. And here's a couple examples, but I need to go to the page about nuclear power to give you. So when we generate electricity, either through hydro or in this case nuclear, you get a lot of steam and hot water. And what do we do with that steam or hot water is important. And so to reduce thermal pollution, large generating plants have cooling ponds or towers where the wastewater, which is really hot, can return to normal temperature before it's released into the lake or river. So we don't want thermal pollution. So let's see which one of those deals with that. Returning cooling water directly? No, that would heat up the lakes and rivers. Returning cooling water to an underground storage cavern? Not usually. Using cooling water to cogenerate? No. Both B and C are assuming that the water is cold. It's not, it's hot, and so we need to cool it down. So sending cooling water through ponds and towers before it's released. So we cool it down, which is what this picture is showing you in your textbook. Oops, that's the other one. Good, I need this one anyway. So anyway, your book has a good picture of that. Let's go to our short answer question here. Label the following parts of an electric motor: armature, brushes, commutator, magnetic field. So we hook a power supply here. Maybe we'll copy this to my PowerPoint so I can draw on it. There it is. And let's draw on it. So we hook up our power supply here, a battery, and this electrical current will flow through this wire, and that will make this into an electromagnet, so a north and south. And so this spins, and it's called the armature. The armature. Now, as it spins, this thing here helps to change or reverse the current. Right now, if the current goes in this direction, this will be north, and down here will be south, and it'll spin away. This is our permanent magnet, like a horseshoe magnet. So P for permanent magnet. So if this permanent magnet had a north end, it would spin in this direction because north and north push away, and then this would be south, and it would pull. But then we want it to keep going in the same direction. So this commutator is what this is. It's a split ring. Will reverse the current in the electromagnet. So once it gets here, it's going to turn, and eventually it's going to be south, which will keep pushing it. So this is the commutator. Commutator. And let's see, what else do they want us to label on here? field magnet, I showed you that, commutator, brushes. Let me show you the brushes. Back to my PowerPoint. So the brushes are this thing right here that sort of touches the commutator. So our brushes are right there. Electrical contacts right here where we hook up our battery. Let's keep going through the test. Next, it wants us to arrange the following in order of electrical distribution into the home. So let's copy that. Let's go to our PowerPoint. Let's add a new slide. And let's get a picture to help us. So step down transformer, branch circuit electrical appliance, power meter outlet, breaker with fuses, electrical main breaker. So let's look at this. So here's the power generating station. The first thing that comes up is something called a step-up transformer, which boosts the electrical energy. Okay, so that's not there, so nothing yet. Then it goes to substations, and eventually before it enters the house, it reaches a step-down transformer, which bumps the voltage down to 120 volts in North America. So that's our first one. Step-down transformer is the first one. Next, let's go back to here. Next, as it enters the house, we see this. So from the step-down transformer, it reaches a meter, okay, which records how much electricity you use. So that would be the next one. Power meter. Next, let's go back to the picture. Service panel for circuit breakers would be next. Here's what that looks like. And then once we get to the house, power supply, main circuit breaker, and then each line has its own, then outlets, and finally appliances. Okay, so let's go back. Oops, PowerPoint is where it is. So this A, D, G, B, F, E, C. Okay, so A first, then your power meter, D, then the main electrical breaker, G, then a branch circuit, and then a branch circuit with a fuse, then the outlet, and finally your electrical appliance. So that's how it works coming into your home. Next, give the full name of the proper symbol for each. Electrical energy, that would be a watt. And electrical energy, joules per second, or electrical power is watt. Electrical energy is joules. And so that's how that works. These are EnerGuide labels. They help us tell how good the appliance is at utilizing energy. And this little thing here, this little symbol, tells you if you bought this appliance, here's where it sits on a scale of the most efficient, which means it only uses 264 kilowatts in a year, versus worst, which would be 1,000. And so this appliance, if you bought it with this sticker, the device would be closer to being one of the worst ones. It wouldn't be very energy efficient. Write the proper formula for each of the following. Finding power when you have current and voltage. So power equals current times voltage. Find efficiency with input and output. So efficiency equals the